If we have the equation x squared equals minus 1, we know there's going to be no solution to that because root minus 1 doesn't exist. So we can write root minus 1 equals I, or minus 1 equals I squared. Complex numbers have real and imaginary parts in them. We usually write z equals a plus bi to describe a complex number. Now, using this, we can solve equations that were previously impossible. For example, x squared plus 4 equals 0. We can rewrite that as x squared equals minus 4. And that can be simplified to x equals plus or minus root minus 4. We know that I equals root minus 1. So if we sub that in, we get x equals plus or minus root minus 1 root 4. This leaves us with plus or minus 2i. So let's do some example questions. We'll start off with addition. Let's say we have 3 plus I plus minus 2 takes 6i. For the real side, we can say 3 take 2, and for the imaginary side, we can say I take 6i. This leaves us with 1 take 5i. For the second question, let's say 2 plus 5i plus minus 1 take 3i. For the real side, we can say 2 take 1. And for the imaginary side, we can say 5i take 3i. This leaves us with 1 plus 2i. Okay, let's move on to some multiplication. Let's say we have 1 plus I times 2 plus 3i. If we expand this out, we get 2 plus 3i plus 2i plus 3i squared. And now we know that I squared equals minus 1, so let's substitute that in for I squared. Then we get 2 plus 3 times minus 1 plus 5i. This gives us minus 1 plus 5i. Okay, let's do another one. Minus 2 take 3i times 5 take 4i. Here we get minus 10 plus 8i take 15i plus 12i squared. If we substitute in I squared equals minus 1 again, we get minus 10 take 12 take 7i. That gives us minus 22 take 7i. Okay, in this part we're going to equate real and imaginary parts. So let's say I times a plus bi times 2 take 3i equals 6i take 1. So we're going to find the value of a and b from this. We know that a and b are real numbers, so we can just separate them up like we did in the last questions. So let's start off by saying I times 2a take 3ai plus 2bi plus 3b, because minus I squared times minus 1 is just 1. So if we expand this out now, we can say 2ai plus 3a take 2b plus 3bi equals 6i take 1. Now if we take just the imaginary parts of this equation, we get 2a plus 3b equals 6. And if we take only the real parts of this equation, we get 3a take 2b equals minus 1. Now we're going to do simultaneous equations to solve this. So when we take away the bottom one from the top one, we get 13b equals 20, and b equals 20 over 13. Now if you substitute that back into the equation and put it in your calculator, we're going to get that a equals 9 over 13. Another important thing to know about imaginary numbers and complex numbers is the conjugate. You can write it as z equals x plus iy. The other solution will be the conjugate, and that will be x take iy. So if z equals 2 take 3i, then the conjugate is going to be 2 plus 3i. Now, if z equals 9, then the conjugate is also going to be 9, because there's no imaginary numbers in it. If z equals minus I, then the conjugate will be positive I. So why do we need the conjugate? Well, if we have x squared equals minus 4, then x is going to be plus or minus 2i. So the conjugate accounts for both the plus and the minus. Let's look at another equation. X squared take x plus 4 equals 0. If we have x take a half squared plus 4 take a quarter, we can see that x equals plus or minus I root 15 over 2 plus a half. You can see that a half, or the x part of the solution, won't change. However, the imaginary part has both a plus and minus, which is why we need the conjugate.